Hello everybody, and welcome to my talk. Thanks for being here. My talk is about hardening bootloaders, or rather the lack of hardening in some respects. My name is Ahmad Fatoum. I work for Pengutronix. We are a German Linux consulting company. We help customers with everything around embedded Linux, porting bootloaders, writing kernel drivers, and getting Linux with a mainline software stack running performant on the hardware. In the last years, a lot of projects start being projects that want to implement some scheme for secure boot. And during these years, I had the chance to look a bit into these projects and see the challenges that face bootloaders to be made secure. So for those who didn't have such projects, or just as a refresher, a common way this is done is with a verified boot chain. And in that setup, every component verifies the next component, starting with some hardware root of trust. This is usually electrically burnable fuses inside the chip. These are burned with a public key in the factory, and from there on, these are used on every boot to verify the bootloader. This verified bootloader has a public key inside, which is used to verify some container image for the kernel. And this container image in turn will often have like a hash or a root hash for the root file system, with which the kernel can verify that the root file system is really authenticated and it's really coming from whoever had the keys to sign this boot chain. And as you can see, if you can mount an attack against the bootloader, all verification steps after it are useless, because from there on you can just flash your own software. And because of that, we should all have, if that's our use case, have a vested interest in securing our bootloaders. So you can just disable verified boot, so to speak, with mounting an attack against the bootloader. How that fares in practice, I want to show you today with 4 exploit examples. And yeah, we will look at how an attack could be mounted on the bootloader and look at the takeaways and what could have been done to prevent this attack from happening to your system. And yeah, so let's start with the first one. This was something I ran into a few years ago. It was not a new project, but it was new for us. And when I looked at it, it was a system that implements secure boot, a verified boot chain, not unlike the one that we have seen. But it had the environment in eMMC, and when I looked at the U-boot environment, I saw it had a variable fit address, which is the load address for the fit image. And that's not really something uncommon with U-boot, so you have a lot of these hard-coded addresses where you load stuff, and normally you put them far away from each other so they don't overwrite each other. And I figured what would happen if I just change fit address to point at the load address from U-boot itself. Hopefully that would result in an error. It did result in an error. It resulted in a crash because the fit image was just executed. So there was no protection whatsoever. And this happens before verification. So the fit image is loaded as a whole into memory and then verified to avoid check time of use attacks. But that also means that someone could just replace the fit image with their own code and just run it and exploit everything from there onwards. So this is really bad, but there are some important takeaways here. For one thing, the U-boot environment is never authenticated. There is no upstream support for authentication. So you must really look at what you actually allow in your U-boot environment. That's called whitelisting. Another thing is U-boot has this software mechanism for reserving memory blocks that was copied sometime from the kernel, but it didn't help here. I'm not sure why. And really, there should be like hardware protection mechanisms, but none prevented this. But there were also some things that went right, that this was not a full system exploit because U-boot was running at a lower privilege level. So if you had at the highest privilege level some encryption keys, for example, these were at least secure, but the rest of the system, starting with U-boot, the kernel, the user space, that was all compromised by a very simple attack. And because of that, yeah, you should do U-boot environment whitelisting. There is a command for that. It's called env-import. But it's very cumbersome to use. So it takes an address in memory. So you actually have to manually load the environment at some memory address, hard-coded, and then you call env-import at that memory address. And if you make these critical features so cumbersome to use, it invites error. And it would be much nicer if you could just have like a global whitelist and say, these variables are important for me, these are allowed to be to come from the environment, from the runtime environment, and the rest shouldn't. But there is no way like that to do that. Another way would be to have like a dedicated boot state store, like barebox uses by default. And I believe you can also do it with U-boot, with these boot count variables that sit outside of the environment. But if you use the normal way, you absolutely have to whitelist what you are loading from the environment. Then there is the elephant in the room. Why was there no hardware protection? And it's not for lack of support for memory management units. Support for memory management units has been part of ARM bootloaders for many years because you need them to actually enable the data caches. So if you want to boot fast, you need memory management unit support. But no one bothered to actually use it for protection for many years until this year. So this year we had the first U-boot release just last month, actually that uses the memory management unit for protection. And read-only data is now, you can guess it, read-only. And executable data is not writable by default. And stacks are also not executable by default. Okay, default is a strong word. It's not enabled by default. It's there, but you need to enable it yourself. And it's only available for ARM64. In barebox, it's sitting in master and will be part of the next release. There, it's enabled by default also for ARM32, so let's see what will break. I guess there will be breakages because code just assumes that you can do self-modifying code. But yeah, that's a small price to pay, some breakage that can be fixed to get these bootloaders more secure by default. But of course, this is not like rocket science. This is what Windows had in Windows 95, which started for the first time doing isolation for kernel space. There is a lot of stuff that can still go wrong, even if you have write XOR execute, which means you don't have memory pages that are both writable and executable at the same time. And yeah, so we are rather at the level of 2006 or something. 2006 or 2007 was the time when return-oriented programming as term was coined. So where once stacks have started to be non-executable, attackers needed new ways to get their code executed, and they started attacking the return pointers that are on stack. And the whole system of countermeasures against that is called control flow integrity, and there is no support for that whatsoever, as far as I know, whether upstream or in publicly available patch sets for U-boot or barebox. So you are still susceptible to these attacks that have plagued user-space software for the last 20 years or so. There is one mechanism that you could call control flow integrity if it was actually implemented correctly, which is stack overflow protection. So that's a very simple concept. You put at the end of your stack frame a random value just before your return address. And then the compiler inserts code that every time you exit from a function, it verifies that this value has not been overwritten. Because if it's overwritten, then you had a stack overflow and someone wanted to mess with your return address. And in barebox, it's implemented, but for many platforms, there are no hardware random number generator implemented yet. For actually, you must randomize it so an attacker doesn't know about it. I implemented like 6 random number generators this year, but something like the IMX8 or the Layerscape, the CAM unit for those, that's not supported in barebox for 64-bit yet, so you can't use it. In U-boot, the situation is a bit more dire. It's never, ever randomized. It's always this fixed hex value, and an attacker who knows that can just use it. And yeah, it's nice for catching programmer errors, but it's completely useless for actual security hardening. But there was a positive side, which is you didn't exploit the whole system. And really, with the state of hardening that you have for bootloaders, you don't want to run all that code in your highest privilege level. You want to move everything out of the highest privilege levels to a lower privilege level. On IMX8, it's done by default, so the customer, even if they didn't do this intentionally, benefited from it. Only U-boot SPL ran at exception level 3. That's the highest privilege level on ARM. That's the one that's very down. That's firmware and secure monitor stuff. And everything from the hypervisor, the kernel, the user space was, of course, compromised. But at least the encryption keys were not compromised. So it's at least a small win. But it's not for free. You actually have to look how your platform does it. So if you say, I want to boot faster, I will do Falcon boot. Falcon boot often works by just moving all of U-boot into the highest privilege level, doing everything, and then at the last step, it loads the TFA and loads the kernel and so on. And this way, you have moved a lot of code that would otherwise sit outside of the trusted computing base back into the trusted computing base, where it could be exploited and used to mount attacks against your system. This brings me to my second example. You might, so I spent some time with the titles. I hope you appreciate them. You can guess what this is about. But yeah, it's a very short story of 4 acts. The first act is you are a bootloader and you want a file system. You are a bootloader with a GPL2 license. So yeah, you will copy the file system from Linux. And the second step is, after you have ported it, you watch how Linux developers, researchers, users collaborate on fixing memory safety issues that are inherent to any complex software, really, in a memory unsafe language. And now the third part, which is very critical, you do nothing, and then you collect CVEs, and a lot of them. If you just search for your bootloader of choice, you will find so many CVEs about file system. It doesn't end. And it's really a thorny issue because file systems are easily the most complex parsers that you have in a bootloader. They are very complex, and even in Linux, where you have like these nice hardening mechanisms for like new ARM revisions that I haven't seen and will probably, as an embedded developer, only see in 20 years or something, even there you can only mount file systems as root, or you need some contraption to do it for you. And in a bootloader without all these hardening measures, you should really not just mount file system you don't trust, even if you had a perfect story of taking patches from the kernel and applying them to your bootloader. At least Linux developers, or Linux users rather, have a way out. They can use something like the mcrypt or the mintegrity to do authentication of the to do verification of the file system image at the block layer. So you can verify, okay, I can verify this image at the block layer before I actually need to parse the file system, and only then the file system is mounted. That's good. That's something you should use under Linux. And we did use it in this diagram with verified boot at the start, but it's not available whether in U-boot or in barebox. So the only logical conclusion, I think, is don't use file systems at all in your bootloader. If you are building a secure product, you will just shoot yourself in the foot with it. And it's not like it makes things easier, but it doesn't make it super easy, because there are still a lot of parsers involved even without a file system. And these are parsers that are not copied from somewhere where you could look for fixes, and nobody is thinking about them. So we have a lot of custom EEPROM parsers, which like detect what kind of memory you have, or they detect what kind of board you have, so they choose the correct device tree. You have partition tables. Usually you don't put your fit image just raw anywhere, but you make like a GPT partition table. You have, of course, the boot state in the barebox case, or the bootloader environment in the U-boot case. You have flattened image trees, which is preferred container format for signed kernel image, at least with U-boot and barebox. And the thing with fit images is it's a very complex format. It's not like you really would want to design formats for security-sensitive applications, because you need to do a lot of parsing before you actually get to verification. And if you have in your secure boot path something like USB sticks that you insert, and these USB sticks have like an unlock token, then the whole USB stack is also part of your critical boot path that needs to deal with untrusted input. But let's ignore USB for now. There is a lot of parsers, and there is a very powerful mechanism for finding issues, memory safety issues in the first place in these, which is fuzzing. For those who are not aware, fuzzing The concept is quite easy, really. You have an application, it gets some generated input, and then you see so for example, address sanitizer, undefined behavior sanitizer, and so on, or stack protector, these hardening mechanisms are enabled, maybe in user space, you see if it crashes. If it crashes, you have found a potential issue that you can fix. If it doesn't crash, you just continue the loop. The fuzzer will do instrumentation on your software and find out what do I need to mutate in the input to be able to get into more code paths and exercise code that was not exercised before. And there is really a lot of solutions for that. Some of them are even built into LLVM directly to make it as easy as possible to use without a lot of external software. And yeah, you would think if that's there and it's very useful, you would think people are actually doing that. But I will have to disappoint you, nearly no one does it. So I did a small survey. Coreboot has a proof of concept fuzzer for JPEG boot splashes. Okay, but nothing more. Trusted firmware A, which while it has hardening measures in place actually, it's also used on some system on chips as bootloader, as BL2 in ARM speak, and they don't have any fuzzing for the stuff that they load there. I looked at U-boot. U-boot has a single fuzz test actually for virt.io rings, which sounds really cool. So Google had this research project. Could we attack U-boot running in a hypervisor by doing stuff on the virt.io rings? It's discontinued Google research, and it hurts a bit extra to know the functionality is there, but no one is actually using it for anything of consequence, because that's abandoned research. No one is going to benefit from it now. But yeah, you could actually build on top of it to parse, fit, or partition tables and so on. For grub, the patches were never merged that added fuzzing support. There are, of course, people that are fuzzing it in research project outside this project, but if it's not part of your code base, or there's not an established, like for kernel, there is syscaller, if there is not an established way to do fuzzing against your interfaces, people are not going to do it. And any fuzzing you have are just snapshots in time, and you really need to do this continuously. 2 years ago, when I looked at this, there were no fuzzing support for barebox either. I knew that some people are fuzzing it. I saw research papers about that. But yeah, on and off for 2 years, I implemented fuzzing infrastructure into barebox and wrote fuzzers for the critical functionality. And I found dozens of bugs, which I wouldn't have found otherwise. And I really think other bootloaders would be also ripe with bugs, because these are often unintended, of course, I hope they are unintentional bugs, and they are always in these corner cases, in these error cases that you usually don't hit. I had a very, I think I have a bit extra time. I had a very funny issue where the device tree parser actually overflowed so much that it came back from the other side, and on the other side there was another device tree node. So it was an infinite loop caused by an overflow all around the address space. And yeah, you find very interesting stuff when you start fuzzing. And yeah, these 5 fuzzers, I think there are 6 now in barebox, are of course not enough. People need to write fuzzers for the critical stuff they actually use. I hope it's easy to use now in barebox. You can define this fuzz test macro, and this fuzz test macro will set up a harness and test your function. And there are also harnesses for like block devices, if your code expects a block device or a null terminated string. And if you have some custom format that in EEPROM, a lot of people do that. They have like this factory data in EEPROM and it's their own parser. Yeah, please throw the fuzzer at it. If your bootloader doesn't support it, maybe you should look into how to support it, or just copy your parser and run it in user space and instrument it there, because there's really with C code a lot of bugs to be found this way. Yeah, this brings me to my third exploit example. So we had one about the U-boot environment. Now it's one about the barebox environment. So you might be aware that in GPT, you now have these partition type UUIDs. And that's a whole UUID with which you can describe what kind of partition is that. And then you have like rootfs for MIPS 64 systems. That's actually a UUID that someone allocated. And barebox also allocated a barebox environment type UUID. If you wonder how you allocate these UUIDs, you edit Wikipedia, add it, hope no one deletes it, and then everyone will copy it from Wikipedia. And after a month, you can start writing code that depends on it, and it's now yours. I have seen it work for the barebox environment. I have seen it work for the UBIT environment. That seems to be the way to do it. And yeah, when barebox started making use of it, it was a convenience feature. So if you have configured no environment at all, barebox will look at its boot medium, and if it's GPT partitioned, it will look for a partition with that type UUID you see here in violet. And if it's there, it will mount it for you. Very convenient, unless it was intentional that you didn't configure explicitly an environment partition, because, well, you are a secure boot system. You don't want to load some unauthenticated scripts. Yeah, that was a bit bad. I hope the exposure was hopefully limited, because the boot state shouldn't be part of your environment, and barebox indeed throws a runtime warning if you do it. And you have the ability in barebox to just disable the runtime environment, use only the built-in environment from compile time, and yeah, boot state is separate. But the problem here is this is a lot of should. I have been doing this for a few years. I know you should do that. I am not sure if everyone knows they should do that. And for that reason, after we fixed this issue, I started writing security documentation for the stuff that as a developer is self-evident for you, to make it accessible to users, to know what are the trust expectations, what are the stuff we think you should use, what are the stuff we don't think you should use. And there, it's, for example, spells out, it's in that red square, don't use a mutable environment in a secure boot system, and avoid use of file system in a secure boot system, because you are just going to shoot yourself in the foot with them. A number of these things can actually add it to kconfig. So we have a config insecure option now, which tells you if you're building a secure product, disable config insecure. It won't magically make it secure, but at least it will disable this environment auto-probing. And a lot of stuff is not fully black and white. So, for example, being able to execute commands over fast boot. This is very useful during development or in the factory, but it's probably not something you want in a device in the field, unless you verify like a token. You could have like a USB token, which unlocks the developer mode. Then it's okay. But that's something you as a developer or integrator or like vendor of this product need to ensure. And such kind of options have now a has insecure default kconfig option, which is selected. So you can open menu config, look for has insecure defaults, and then start writing down your thoughts why it's okay for you to keep these enabled. It can be okay, but yeah, someone needs to look at them, and that's one way to make people look at it. And I went through all options that I marked with has insecure defaults and wrote some help text explaining why this can be a security issue. So to get people thinking about it. Because, yeah, that's a bit of a common problem for everyone, is the concept what is secure is different. There is no definition of secure that fits into every threat model. And that makes collaboration difficult. And I hope with that, it makes it a bit easier if people who in their use case see that this is not a secure thing to do, can just edit the help text to help other people. Yeah, and this brings me to my fourth example. This is not something I ran myself into. It's something that I read online, but I see lots of parallels to what I am doing day to day. Of course, not the exploit part. Everything is secure at my side. But yeah, the problems that they are facing. The story is about Nintendo, who for the Wii U wanted to flash these devices in the factory, and they made these memory cards and GameCube memory cards and SD cards. And these had factory bootloaders, which were signed with production keys, and that was deemed okay because, of course, they are going to dispose afterwards of these factory bootloaders. This is not a very strange situation where our customers find themselves in the same situation, because if you are saving using secure storage on your SoC, often you need like a hardware unique key inside the SoC that you can use for this secure storage. So you can't just, if you have cracked one device, you can't use the information you gain there to unlock the secrets of another device. So it's unique per device. And to further protect it, you must actually enable secure boot and lockdown to be able to store these keys. So if you are generating these keys in the factory, you need to have secure boot enabled. And so your secure boot image, your factory image needs to be signed with production keys. And a similar situation was also the case for Nintendo. They disposed of the SD cards, they bent them in the middle, they crushed them, and they threw them away. But we hackers managed to get a hold of them anyway. They physically re-straightened them and stole that stuff to them and did a lot of hardware convincing. And finally, they managed at 20% from this card to dump the firmware on them and get a hold of the factory bootloader. The factory bootloader was a separate code base with its own fresh, never seen before exploits very early in the boot process. And yeah, they could exploit that and disable secure boot, so to speak, on these devices by mounting an attack with that image. Here's a blog article if you are interested. But yeah, this is not an issue that couldn't affect the systems that we build as well. And it goes deeper than that. So factory is only one use case where your security expectation change with the life cycle of the product. There is also development, where you want to have a development shell, JTAG, or whatever. There is a field return. So if a device that was secure booting comes back from the field, it's broken, you need to inspect it, you need to unlock it somehow. If you want to allow your the owners of the hardware really to unlock their device and flash their own software, you also need to have a way to just unlock this particular device for them. And there are different ways to go about implementing these different security expectations. The one that Nintendo went with in this example is having different binaries. There is a very strong argument in favor. The binaries, for example, for factory, lack codes that would only be useful for release and vice versa, and code that's not there can't be exploited. But it increases complexity a lot because you now have different images. It's very hard to test in an automated manner or even manually hardware that you have no way of interacting with over a serial console, and you can just like use it like a user, which is a useful kind of test, but it's not the best test to like catch regressions and stuff. So you want to look at kernel error messages, for example. So console, even if read-only, is very useful. And this extra complexity leads to bugs, as we have seen, or leads to security issues, as we have seen with Nintendo, because that bootloader, even if everybody tried to do their job, it still got leaked indirectly. Another way is to have the same binary, but do runtime decisions. And yeah, this makes handling a whole lot easier because you only have a single image, but it's by far not as convenient to configure as doing it at compile time, because at compile time you can have different kconfig configurations for your bootloader for each type. Then you can diff them against each other and see the differences, but there was so far nothing similar for doing runtime detection of your security mode or runtime enforcement of your security mode. And with that starts the ad segment of my talk. I actually worked on this on and off the last 2 months to try to improve it. I call it security policies. Getting started is quite easy. You create a number of empty files for your different security policies. For example, you call it development, factory, lockdown. Then you can, in the barebox build system, use a new make target. It's called the make security menu config. And it will open menu config for each one of these new files and ask you security-related questions like, do you want to allow console input in this policy? Do you want to allow executing shell scripts? And these are use the kconfig infrastructure, so that they have dependencies on each other. So if you disallow console input, it won't prompt you, do you want an interactive shell? Because, yeah, you wouldn't be able to use it anyway. And it also has dependencies on your build time configuration. So if you have no USB support at all, it won't prompt you for fastboot OEM commands because that's a USB gadget. And that way, these questions that you are asked are actually the questions that are relevant to you. So this is really stuff that you should decide in your security policy. If I am now in lockdown mode, should this be allowed or not? At the end, you get a number of kconfig style files. They start with sconfig instead of config. And these files, when you add them to the build system, which you did in the first step, they are linked into your barebox binary. And then at runtime, you can actually select them by name. So you could like ask if users, you could ask a JSON web token that comes from somewhere, you could ask a trusted application in the secure world, or in this case, it's asking the boot ROM if we are in lockdown mode, and then you can activate this policy as a whole at once. And yeah, the code that actually makes use of it looks like this. It's a single macro. It's called isAllowed, and isAllowed either returns true or false if your currently active security policy allows something or not. And what I hope with that is to address this core problem of individual threat models defining what's secure. So what's secure for person A is not secure for person B. And this makes collaboration very difficult. And it's also a reason why we run into this issue, because a developer will tell you, yeah, of course you do whitelisting, instead of providing you a way to just disallow completely a loading of environment. So the security model is like you do stuff, you stop doing stuff, but you can't just say, no, I don't want environment in any way. And with security policies, this becomes possible. And I think it would allow better collaboration, because people can start adding these allowed macro invocations across the code, but everybody can customize the actual policy according to their model. And this can be audited more easily than C code, which is doing this right now in projects. And after updates, you are actually asked about every new option. What do you want to do with it? Otherwise, your build fails. And that way you always have an up-to-date security policy. Yeah, that concludes my talk. There is a demo about the security policies. I have like some colored USB sticks with JSON web tokens on them that you can insert, and there are some funky LEDs. So if you want to see that and or just talk to me or my colleagues at Pengutronix, please drop by at 17 today. There is another talk about bootloader security tomorrow from Richard Weinberger. So if the topic is interesting to you, I will be there. So yeah, you should come too. And yeah, I have something to look forward to. I hope security policies will make it into the September or October release. It's at version 2 now at the mailing list, but I think it's progressing okay. Yeah, external build system integration is missing, so Open Embedded Core will need support in Bitbake or in DevTool to you actually can manipulate these security configs when you don't have to drop to a dev shell. The fuzz tests, while they are there, they have memory leaks. Bootloaders usually leak a lot of memory because no one cares when you have a 1 gigabyte and you only need to load a kernel. Why care about memory leaks? But if you execute the same code a million of times, you start to care. Yeah, I hope to get these fixed for the existing tests and to apply for Google's OSS fuzz, so Google can throw some compute at fuzzing barebox. Yeah, and in the works is, I think, upstream downgrade protection. Maybe that's something that will be available this year. Generally, I wish there would be a lot more focus on hardening and fuzzing bootloaders and firmware, and more documentation for users. So I could write this documentation for barebox, and it's still incomplete, but I don't really know how to do it for other components because I am not at an experience level that allows me to know what you really should do. So it would be nice that documentation is written for non-experts. Fit images are a very complex format. I wish we could verify it without parsing. That's not possible generally right now. And yeah, maybe in the future, critical components will start being written in memory-safe languages, at least partially, because yeah, there is a lot of stuff that can go wrong and that indeed goes wrong, and security suffers for it. And yeah, so we have like 5 minutes left for questions. Thank you.
Thank you for your talk. So one big piece of it was, we're trending behind on importing patches from the kernel and things like this. And I think the PC world has sort of made the same, gotten to the same conclusion, and their solution to it is unified kernel images. So not having a bootloader anymore and just jumping straight to the kernel. Do you see something like this having potential in impact?
Yeah, so the question is, did the x86 world do it right with like unified kernel images and not having a bootloader? So you still have the bootloader, it's just your UEFI firmware. If you are on ARM, that's Tiano Core or U-boot currently. And yeah, if it's still the implementation of U-boot's fat file system that you are using. It doesn't matter if you put UEFI in the middle, you are still using it. And I don't have much trust into the FAT implementations in UEFI firmwares. So not even security-wise, but just FAT is not journaled. U-boot doesn't have even journaling for the file system it has. I don't think it's really powerful safe thing to do. So I think there is a safety problem before there is a security problem in actually using it. Yeah, you just shift the problem elsewhere. But then you can say you can do nothing about it because you don't have the code. Thank you.
We're doing full scale image verification on IMX CPUs right now, and pretty easy. I think the fact is like 3 lines ago. What is the issue with creating a generic solution for doing that?
Thank you. So the question was, there is full image verification on IMX. Why can't this be extended to other platforms? So for one thing, as you said, you need a patch for it. And there is actually a spec now that describes fit images and how verification should work. So you should really extend the spec to support for it. Then there are some open questions. For me, I haven't used this on IMX, like how do you deal with padding, for example? What is now the padding scheme that you use for the signature? How is it yet now SHA-256 for the actual algorithm? I don't know where this information is at. So you need to specify how it should work so others can implement it. But yeah, the same scheme we have on IMX, I would love to see it on other platforms as well, so we can just get away from having to pass this complex format before we can do verification. Okay, if there are no questions, you can find me in the hallway or at the technical showcase later today. Thank you.